Okay, module 4 is going to be on interest. Okay, and the main form of interest that we're interested in is compound interest. There's other forms. Simple interest is a good way to get you a feel for it, but we're going to skip that. We've already seen compound interest in action with annual compounding. And that's the most common type, and especially when they test you on your understanding of interest and how it's computed, they make you do interest compounded in different ways. Okay, let's just formally define interest. It's a payment, so it's a payment to a lender. Somebody who loans money doesn't just do it for free. They usually want more than they loaned you back, and that difference is interest, the amount they get paid essentially for loaning you the money. So interest is a payment to a lender for the privilege of borrowing money. Okay, and actually sometimes it's borrowing other things other than money, but so I'll just put borrowing. Okay. Bullet point. I'm just going to use very general assumptions because I don't want to get too much in detail about banking regulations, which I don't even know. Anyway, interest is earned on money in the bank, sometimes not checking accounts, but savings accounts definitely, and if there's other forms of deposits, certificate of deposit and other things where if you put money in the bank can then loan it out on your behalf, and the bank takes a cut, but the interest goes to you with the bank taking a cut. So that's why they're paying you interest on your savings account, because they are loaning out the money that you put in there on their behalf, and they're guaranteeing they'll get it back for you, so there's no worries. Okay. Interest is earned on money in the bank. Since the bank loans out the money on the account holder's behalf. Another type of interest that you're going to, not type, but another way interest is going to become involved in your dealings with the bank is when you borrow money. When you take out a loan, then you have to pay back the loan plus interest. That's a little bit trickier. In theory, what we're going to do could be applied if you're going to pay it all back in one lump sum, and we could figure out that total amount you got to pay back at the end of the loan. But usually you pay it back in increments every month. You're making a monthly payment, and because of that, it gets more complicated. So for the purposes of this lecture, just to get you a feel for interest, we're always going to think about it as just money in a bank account earning a certain amount of interest compounded in different ways. I'm going to erase here, and yeah, so this is just a general explanation of interest, but there's kind of a standard way that they write out the equation that we're going to use. So these are terms and symbols. P, capital P, is the money borrowed or deposited. Let me put that. Called the principal. The same spelling as the principal of your school, not the principal, not our moral principles. Now, R stands for rate. They use that for the interest rate. Typically given as an annual rate, an annual percent rate specifically. Which is abbreviated APR. We're also going to have an acronym APY, and they're going to be very similar and possibly confused with each other. We'll try to keep it straight in this lecture. T is the number of years over which a loan or a deposit accrues interest. Accrue is a term used by banks oftentimes for building up, accumulating. And then N is the number of times interest is calculated and added. That process is called compounding, so let me put that in. Calculating the interest and then adding it to the account is called compounding, and we're going to do it several times per year in certain situations. So N is the number of times interest is calculated and added or compounded each year or per year. The duration of time between compoundings is called the compounding period. Okay, let me go back and underline the important words. Principal I forgot to write interest rate and also annual percentage rate, annual percent rate. T is for time, for number of years. That's not something I need to underline. Compounding is terms that were relatively fresh. I could underline this, but again, there's going to be a thing called APY, and we have to make sure we can distinguish between APR and APY. Don't worry, it's not that bad. Okay. Oh, and then A. Actually, hold off. Those are good. Those are the symbols we're going to use. All right. That had a lot of explanation as well, a lot of terms, but I did want to summarize here. The same thing I just said, but I want to kind of organize. So P is going to be principal, that's a capital P. R is your interest rate as a percentage. T is time in years. That's going to be standard. We're always going to use years. Even if you're compounding monthly or daily, T is going to be for years. We'll see examples in a bit. N is compounding periods per year. And then we are going to see a capital symbol, a capital A symbol in our formulas, which will just be the amount. In the account after T years. So we're just going to go straight to the end period, the end of the term. Okay, let's talk about compounding periods. So this is going to just be a box for you to remember those letters that we're using and what they stand for in the formula in a more concise version than the one where I wrote out definitions and explanations. And then compounding periods. Based on how it's described, you can figure out n right here, that's going to be in formulas, the number of compounding periods per year. Let me see. I'm going to make this big because it's going to be words in here. For instance, we actually encountered compounded annually, which is once per year. And n is the number of periods per year. So if you're compounding annually, how many are you doing per year? Just one. So we're going to see problems where they say compounded annually. We're also going to see other compounding periods. Oh, sorry, maybe I should say annually. Yeah, let me make it into an adverb. Annually. Next is going to be semi-annually. Semi means half, like hemisphere. It's hemi and semi, same prefix, essentially. Means every half year, which means 6 months into June, you're going to compound, and then again at Christmas, around Christmas, you're going to compound. And that means twice per year. So n in the formula is going to be 2. Write in the remaining ones that we're going to be dealing with. I'm going to stick to some basic ones. I'm not going to go get crazy with this, but it can, in theory, get crazy. So we're going to deal with quarterly, monthly, daily. In theory, you could have every minute of the day, every second of the day. You could have what's called continuous compounding, meaning you're chopping time up into smaller and smaller time intervals, and when you do it continuously, you're chopping up infinitely, and to do that you need calculus. So continuously compounded interest requires calculus. We're not doing that. We want to get a feel for the basics, and I'm just going to go down to daily. I'm not going to do per minute, per second, per hour, but I do want you to be familiar with these. Okay, I'm going to skip to monthly. All right, monthly means every month. How many times per year is that? 12. Perfect. Daily means every day. How many times per year would that be? How many days in a year? 365. Okay, we're not going to deal with leap years, so we're going to stick with 365. Let me backtrack. Quarterly may not be a term you're familiar with, but oh, I assure you, financial institutions and banks use it a lot. Quarterly is commonly how you chop up the year into 4 quarters, fourths of a year. That's every 3 months. Since there's 12 months in a year, you chop it up into 4 pieces. Every 3 months is a quarter. That means you're doing it 4 times per year. All right, and that, again, that's a very common one where they do financial stuff. They calculate things every quarterly. They have to file reports quarterly. They have to do other things quarterly. Okay, yeah, I can fit it here somewhere in your notes. Yeah. Compounded n times per year. There's going to be a formula for the amount in your account. I'm going to just write the formula. I want all this stuff organized in one place in your notes, and then we'll start doing examples. But here, the formula I'm going to use is A is equal to capital P times 1 plus R over N to the N times T. It'll be an exponent. I'll go over the calculator and how to do it on your calculator. Okay, and that's the main formula I'm going to be using. there's going to be a, not really, a separate formula, but not really, for compounded annually. Now recall, compounded annually means just once per year. That means n is 1. And this formula still applies. Don't write this down, because I just want to talk about why I'm going to write a different formula, even though I don't have to. If I wanted to just use n is equal to 1, we would have 1 there. R divided by 1 is just R. So this whole thing would just be R. Again, don't mess up this formula. I'm going to copy it over there, but I just want to talk about it over here. Well, maybe I should just do it over there. No, that's fine. Yeah. Let me do it over there. Sorry. I changed my mind. Don't mess this up. It's perfect the way it is. Let me mess this one up. Okay, and here I'm going to erase because we're not going to use the same formula. Sort of. Okay, so this formula would apply here, but again, if we actually put in the 1, since compounded annually means n is equal to 1, we could just fill in the 1 and see what happens to the formula. It definitely makes it simpler, and let's make it simpler. This n right here, r divided by n becomes r divided by 1. R divided by 1 ends up just being r. There's another n in the formula. N is equal to 1 for that n that's in the second place it appears in the formula. It'd be 1 times t. And 1 times t would just be t. So when you're talking about compounding annually, you end up just doing this. It is equivalent to this with n is equal to 1, but I'm going to write it as a separate formula so you don't get bogged down wondering about here. But this does still apply. It is the same formula, just with n is equal to 1. All right, I'm going to pause here and I'm going to start doing examples. Okay, let's do an example. A deposit earning 5%, which is not realistic, by the way. They give you like 1, 2%. They're not giving you 5%. But I'll be giving you some unrealistically nice examples. A deposit earning 5% annual interest. That's your APR, your annual percentage rate. Again, we're not going to emphasize APR, but we will talk about APY. Annual interest rate, or annual interest compounded annually. We'll have, this is more of an explanation, 5% of the balance added to the account each year. That's what it means to compound annually, and in the future you won't have this explanation. This is more of an explanation that we talked about earlier, but I want it in this first problem of ours. Suppose $2,000 is deposited into such an account, one that has 5% compounded annually. In such an account. Calculate the balance after 3 years. Okay, and all of these will assume the money sits there untouched and just earning interest. Later on we will be dealing with situations where you're going to be making monthly deposits or monthly withdrawals or things like that, but for now, put a bunch of money and let it sit and let it earn interest and find out how much is that in the account after 3 years. Okay, we did this before, where I talked about how this is going to be doing. We're going to be using the formula, the appropriate formula from here, eventually, but let's just talk out this process again, because it is something I did before in the previous lecture. Your year starts off at 0, 1 year, 2 years, and 3 years later. This is almost identical to what I did previously. And your balance will keep track of there. Slightly different in that this time we have $2,000. Dollars, but I'm not going to put dollar symbols sometimes because I don't want to clutter up you. I want a clear view, but obviously dollars. Okay, we're going to add 5% to the balance each year. So that's your starting point. Year 0 is the starting point, and then after the first year, you've earned interest of 5%. You don't want to use 0.05 in this situation. You want to use 1.05 because again, you're keeping your money and you're adding interest to it. So it needs to be, you're calculating 105% of your previous balance. So we want to increase the amount by 5%. My calculator's over there. This is not the question, by the way. The question is to find just the ending point. And again, we can go straight to that and do it, and which we will. You get 2,100. Go ahead and fill out the rest of this table doing the same thing. You're going to take that 2,100 and increase it by 5%. Figure out what you're going to multiply by and then do the third year. We'll do it the long way this time. And then in the future and on the homework, you're definitely not going to have to do that. Unless I want to know year by year. But more often I just want the balance at the end of the period. And we'll just go straight to one of these. Compounded annually means ultimately we'll be doing this. But I want you to understand what this formula is doing over here. All right, pause it here if you want to take some extra time. Balance at the end of the second year would be increasing 2,100 by another 5%, so multiplied by 1.05 again. And I got 2,315.25. No, wait, what happened? No, sorry. I jumped ahead. I did both of these computations and I have both of them here. 2,205, I jumped ahead. Okay, I got it. Then for the third year, end of the third year, another 5% increase. So we increase that by 5% by multiplying by again 1.05. And that's where we get what I had written earlier. 2,315.25. Again, you're browsing to the nearest cent if needed. We did not need to do that in any of those computations. All right, that's a long way, and we got our answer, but let's start taking advantage of this formula, which just jumps straight to the end of the 3 years. Now, we could use this one, but the compounding n is going to be 1 because you're compounding once per year. This is compounded annually. So we can use the somewhat simplified version of this formula where n is equal to 1 that we talked about. So we're going to use this one. Sometimes it helps you to organize your thoughts and your principal and rate and that kind of thing. Our principal, the money you invest or put in the account in the beginning, $2,000. That's a comma, not a decimal point. Okay. Our rate. R stands for rate. Now, it's given as percentage, but when we work with it, we're using the decimal form like we did here. So be aware, R always is a decimal form. Basically, all percent we just start dealing with in decimal form because that's what it means. 5% again is, it literally means 5 over 100, which is equal to 0.05. So that's what the rate is, 0.05, which is equal to 5%. But we need to use the mathematically accurate version of it, 0.05. T, the number of years, and we want 3 years. And we do not need to do n because n is equal to 1, and we're using this formula right here. The amount is what we're trying to find at the end of the 3 years, so why did I write this so big? Let me do it on the side. Let me just move this real quick. Not making good use of my space. Hopefully your notes are not too crammed and disorganized. Alright, here we go. You don't need to write the formula every time, but you know, early on in this process. I want to see it right here and fill in what I know. I don't know A, I'm trying to find the amount in the account after T years. Principal goes out there. 1 plus 0.05, and then raised to the T power 3 years. The 1 plus R is what we've done. It's essentially the percent increase formula that we did earlier in the last lecture. And if you want, you don't have to write. If you're writing, showing your work, you know, in theory, the more is better, but I don't need to see that. If you know what 1 plus 0.05 is, you can go straight to that. It's the same factor that we've been using, you know, when we do a percent increase. So you can go straight to that. No need to write this. You can skip that step if you want. I don't know why I crossed it out. I thought I was gonna. I literally thought I could just undo that. Like a computer. I'm too used to working on my computer. 3 there. I'm not done here. 3 of those factors, because that's 1, 2, 3 multiplied together. That's where that 3 comes from. So it's literally the same thing that we just did here to get there in multiple steps, but in one step. All right, let me pause there and start talking about the calculator and exponents and how to work our calculator. This is what your calculator will look like. TI-84. You might have an 83. I said that an 83 was acceptable. If you have an 84, there are different versions. I have a plus silver edition. There's just a plus. There's a, I forget, all kinds of editions. As long as it has TI-84, it should be relatively similar to this. Okay, and then I'll do an 83 lesson because 83s are a little bit different. But right now, this introduction applies to both. I'm going to do some basic stuff first before we're ready to deal with our computation. So this is your first lesson on this calculator. All right, first of all, each key has a primary function. This is your 0 key and 1 key and 2 key and so on. Enter to like evaluate something, meaning do the computation you entered. But above each key in blue on mine, yours might be a different color, but it's color coded. There's a secondary function in blue. And to get that secondary function, you're going to use right here, color coded, the second key, which is colored in blue. Again, your color might be different. There is a green, a third option for each key in green, and here it's the alpha key, but we don't use that. We're just going to use the secondary functions of keys sometimes. But anyway, here's an on button. Turn it on, and it gives you a little introductory screen or a splash screen. If you want to turn it off and save your battery, the off key is the secondary function of the on key. So to get that, I don't hit on again, I got to get the secondary function. So I'm going to hit second. Once it's in secondary mode, that little indicator indicates that you are now in, you know, like it's like shift. So you're now in shift mode, and then any button you press will be the blue secondary function, in this case off. Perfect. Let me turn it back on. To clear the screen, you want to hit clear over here, and you can do some computations on here. 2 plus 3 is 5. Okay. I want to mention, because a lot of times you put it in your pocket or your bag and it accidentally hits a key that you don't want to, like butt dialing. Okay, so if, for instance, you accidentally hit graph, and we're not doing this, we're not doing graphs on here, but if you accidentally hit this key, let's say, and it takes you to a graph, you want to get back to the main screen. And to get back to the main screen, you're going to quit out of the graph mode. And it's all quitting. Just quit right there, which is the secondary function of this mode key right there, quit. So I'm going to go second. There's your secondary indicator. Quit. Takes me back to the main screen where it has my previous computations. If I were to accidentally hit this button, for instance, it takes me to this weird table that I don't want to be in. So I can quit out of it, back to the main screen. All right, I want to clear screen. I like my screens blank when I do things. And let's do this computation. 2000, count your zeros, times right here. It's going to show up as a star. And the parentheses are more for readability of what I wrote on the board, so you can distinguish between the principal and the factor. But it's not necessary. You could put it here. There's an open parentheses here. And in the future, we will be making use of the grouping parentheses. We could do that, but more likely it's not necessary. And if I want to delete, it's not easy to do because I could go character by character and delete the whole thing. Okay. But either way, with parentheses or not, that's my factor. It's going to follow order of operations, so sometimes my parentheses that I write on the board are not necessary for the calculator to interpret it correctly, but sometimes it is, and I'll try to emphasize when it is. Anyway, the main point of this, exponents, right there, your caret button, C-A-R-E-T, not like a food carrot. Okay, you click that, and on the TI-84, it'll give you a little, oh my god, I hit the wrong button. Give me a second. Okay, I just clicked the wrong button, but there we go. We're gonna click it, and it gives me a little box raised for an exponent. We'll hit 3, and there it is. That's it. That's the amount in our account after 3 years. Let me give a quick lesson to the people with the TI-83, but the off button and the secondary function stuff still applies. It's just going to be appearing on your screen a little bit more crudely. Let me put it that way. Sorry about my voice being probably a different volume than when I do lecture on the board. I'm sitting on my computer doing this, so I don't know how to, oops. I don't know how loud to talk. But anyway, real quick, same button, same off. Well, this one's coded yellow, but for the secondary functions, no big deal. On, let's clear it. 2,000 times 1.05. Here, I just want to mention it's the same thing, the same caret button for exponents. It's not going to give you a raised box though. It's just going to give you a caret symbol. It's not as advanced. And I want to put 3, and that's good. We'll have to be a little bit careful in the future of other things when you have a product in your exponent, let's say. So we will come back to this a little bit, but we're good. For this one, it's basic, and it just doesn't appear as a raised 3. All right, we're good. Okay, so 2315.25. Rounding to the nearest cent, but it came out to an exact 25 cents, so there was no rounding in that one. There will be in the future, so make sure you remember you're rounding to the nearest cent. Okay, we'll do the next example. Next example is going to involve some sort of other compounding, not annually. We'll do quarterly at first, and then we'll get a feel for that kind of thing. Okay, a deposit earning 12%. Again, no bank is going to give you 12%, but let's keep it nice and round for now. 12% annual interest. They generally will give you annual interest despite the fact that in this case we're going to compound it quarterly. Compounded quarterly. Each quarter of the year, meaning 4 times per year, every 3 months, but we don't deal with the 3 months, we're going to deal with the 4 times per year. Compounded quarterly, we'll have, again, this problem will have an explanation about how it's going to work in the problem itself. We'll have 12 divided by 4 is equal to 3% of the balance. I'll explain this more once I finish writing this problem. Add it to the account. Each quarter year, which again is every 3 months. That explanation about how it works is not going to be in future problems. You'll understand in the future, compounded quarterly is done in this way. Okay, suppose $7,000 is deposited in such an account. Calculate the balance. After 2 years. Okay. So once again, let's do this. I gotta do it weird. I don't have this. I can grab it over here. Somewhere in your notes. Let me see. going to be a longer list this time, that's why I need to make a lot of room. Okay, so even though it's 2 years, I'm not going to have 2 lines because I'm going to have a line for every single compounding. So this is year 0. And year 1 is going to be a little bit later, and I'm going to show you how business entities will label their time periods. After a quarter of a year, they refer to that at the end of Q1, Q for quarter. So that's the first quarter, the end of the first quarter, the end of the second quarter, the end of the third quarter, and after 4 quarters, that's 1 full year. So I'm going to label like that. I mean, you know, even though it says year, that's 1 year, but then in between I'm putting quarter 1, 2, 3, and then the full year. And same thing, they would label Q1, Q2, Q3. That's the first quarter of the second year, because you're leading up to the second year. It's 2 years. Okay. We're not doing this. I just want to organize it and talk about each little compounding period 4 times a year, each quarter. Sort of do what we did in the last example, talk about what factor we're applying, and then jump to our formula and relate that table and what we would do there to the actual formula, which does the same thing. Okay, so we'll get there, but let's just make sure we understand this. Okay, 12% is your annual percentage rate, so that's your APR. And what they do is, that's for 1 year, but since they're going to do it 4 times per year, they're going to chop up that 12% into 4 equal pieces. That's what this is. You don't need to know this term, but it's called the periodic rate. 12% is your annual percentage rate. These are not terms I'm going to test you on, so don't worry too much about it. But you know, to distinguish, you have your annual rate 12%, but you're going to apply that 4 times per year. So they want to know how, you know, what percentage are you going to apply each of those periods, and you have your periodic rate of 12% chopped up into 4 equal pieces. Again, the 4 is your N. Quarterly, let me jump, I know I'm all over the place here. Quarterly means N is equal to 4 times per year, and that's where that 4 is coming from. That, by the way, is the, right there, R divided by N. That's the periodic rate. We would be doing 0.12, we will be doing 0.12, sorry, that's a 0, divided by 4, and getting 0.03 as our periodic rate. That will be used in that formula. And what are we doing with that 3%? We're applying that every quarter. So we're starting off with 7,000. I'm going to erase part of the problem, but don't lose track of it. It's 2 years. I'm fine, okay. And then I want to increase it by, not 12%, because this is just 1 quarter. I want to do it by 3%. And then I'll get whatever it is I get. Oops. 7,210? Okay. Over the next quarter, what am I doing? Same thing. It's increasing. So we're going to increase it by 3%, a quarter of the annual rate. 7210 times 1.03. 7426.3. And I'm going to put the 3.30 because now we're talking about cents, so I'll write it the usual monetary conventional way. Multiply that by another 1.03. 7649. 0.09. Now I'm starting to have to round figures. That's a rounded figure right there. And so because I'm doing, if I did it this way, step by steps, you know, sometimes the rounding will lead to errors where the final answer is a little bit off from what we would use by doing the formula. So just be aware, we're going to be using the formula to get a more accurate ending balance. But when you do this way, it's a little bit off because that's not exact anymore. That's a slightly rounded figure. But I just wanted you to get a feel for this idea of increasing it, not by the annual interest rate, but by the periodic rate. Okay, and another thing I got to worry about is, even though it's 2 years, sorry, let me put it back in, after 2 years. That's the same sentence that I had erased earlier. Okay. even though it's 2 years, we're not just applying that 2 times. Think about how many times we're adding 3% of the interest. How many compounding periods are there? Meaning, how many times will we do this to get to the end of 2 years? Think about that while I get prepared for our shortcut. I'm not filling all this in, I just wanted to get you an idea of what's being applied. We are not compounding annually, we're compounding n times per year, and quarterly means 2 times per year. Our principal, okay, we can get started. Our principal is $7,000, the amount that you deposit initially. Our rate is the annual rate. We will divide it by 4, but that's part of the formula already. But our annual rate is 0.12, decimal form of 12%. Again, we're going straight to decimal forms here. How did I write it? N is next. We're compounding 4 times per year. And T. T is, again, the number of years. So we are going to use 2 there. But I did ask you how many compounding periods we are going to be applying, and we'll talk about how the formula handles that. Oops. Let's see. Okay. The amount is what we're trying to find, so that's unknown. But we're going to do P1 plus, this time, R divided by N. And our exponent is a product of N times T. Okay, so 7,000 is our P. Rate is 0.1, our annual rate, which is R, 0.12, but we're going to divide it by 4 like we did over here. And so that factor is going to come out to 0.03. And then N times T here is going to be 2 times, sorry, that's wrong. N is 4 and T is 2, right? 4 times per year is what N was. I'm hiding it right now. N is 4, T is 2. All right. These are still nice round numbers. So 0.12 divided by 4, you can do that on your calculator. It's going to be 0.03. You can add it to the 1, and you get that factor that we just saw being applied over here. 1.03, because you want to do a 3% increase, a fourth of the 12%, but you want to do it 4 times per year. And here we go. How many times would you apply it? 1, 2, 3, 4, 5, 6, 7, 8. It's 2 years, but 4 times each year would be 8. 8 compounding periods. That's what this is. You're applying this 8 times. That's it. That's where this comes from. N times T is not just the years, but the number of compounding periods. The number of times you're going to apply that factor. All right, and we're ready to go. I'm not going to go to my calculator yet. I will have to go back there when we talk about how to type this in. We're going to, in the future, not do that. We're going to go leave it like that and type it straight in like that, the factor at least. You'll see in a future example, but this one was nice and round and fairly straightforward. Okay, 867.39, and it rounds down. We are going to have to round our money there. Down to the nearest cent as usual. 8,867.39. That's the amount in the account at the end. Now if you did do it this way, all the way down, let me actually see if I can, yeah, you might get something slightly different at the end because right here we started rounding, and so that's already a little bit off from that computation, and then we might do more rounding, it's a little bit off, and so at the end we might have like 40 cents or 38 cents. So just be aware, doing it this way will introduce errors, rounding errors along the way. This is more accurate, and we're going to go straight with that. But in case you were to work it out all the way down, and you got something slightly off from this, that's why. It's because each time we round to the nearest cent introduces rounding errors, which makes it off from the more accurate answer that just does it, applies it 8 times in one computation. Okay, yeah, I'm going to pause and do another example, and then we'll get into the more trickier things about entering this. Oops, I mean, in your notes, just, if you had written this whole table down 8 times, just where that 8 comes from, you're applying that 8 times. Sorry, I just wanted to add that into your notes for future reference. Okay, just more examples. do several more examples just to get a feel for it, more practice. I'm going to have you pause and then do it on your own first. Not quite yet, though. We have a few more things to talk about, and then we'll talk about a final thing called APY. A bank offers not so nice interest. 7% interest compounded monthly. Suppose we deposit $4,320, again not a nice amount, into the account. And leave it untouched for 10 years. How much will we have in the account after the 10 years? Now this one, I'm going to talk about the computation on the calculator and what we have to worry about and how we're going to type it into the calculator. So this is what this example is for. It is not for us to build a table again and show what's happening. We kind of already know what's happening. We can go straight to our formula. I still recommend you summarize things first. Things we're going to use: P, R, N, and T. P is our principal. R is our annual rate. N is the number of times compounded per year, and we are compounding every month because we're compounding monthly. And T is your time, but in years, not compounding periods. We get that by multiplying the N times the T right there to get, like last time, 8 compounding periods. But the formula takes care of that. T is just straight years. All right, take a moment to fill these out based on the problem. Then you can start writing out your formula and filling in those values, but then pause on entering it into your calculator. We've got to talk about that. But I do want you to be able to set it up at this point. Principal is the money in, pause here, and then unpause. All right, I'm assuming you figured all these out. The principal, the money we put in the account in the beginning, $4,320. The rate, we're going to go decimal form, but the annual rate, 0.07. So we got to get good at these percents to decimals real quick because we're not going to be, spending time talking about it. N, the number of compoundings per year. It's based on compounding quarterly was 4 times per year. Compounding monthly means how many times per year? 12. All right, 12 times per year because there's 12 months in a year. And then again, daily would be 365. You have that in your notes above. 12 for this problem. And how many years total? 10. All right, let's fill this in. Let's copy it down. All right, and the A is unknown. Usually we're trying to find the amount at the end. 4,320 goes in front. That's your principal. You're multiplying by a factor that you're going to get by doing 1 plus 0.07 divided by 12. Let me write that in. Again, decimal form is crucial. And then the exponent is going to be based on the fact that if you're doing it 10 years, 12 times per year, you're going to be compounding it 120 times. So that factor is going to be applied 120 times. Now, I'm going to just write 12 times 10 so you know where things are coming from. But then I have to talk. Okay, so perfect if you did this. All right. If you have any questions or are stuck, text me right now. Pause the video and text me and let's get some clarification. But if not, let's start talking about this. Now, we can start to simplify things before we put into the calculator. However, okay, 12 times 10 is going to be a whole number. Multiplication always of whole numbers always gets you another whole number. So it's perfect. As I said, 120 compounding periods. We already knew that, because I just talked about it. But let's talk about what I did last time. Last time I had a nice round number, and when I did this division, it came out to a nice round decimal. No rounding was necessary, and I added the 1, and it was fine. It was beautiful. But this time it's not going to be so nice, and that's deliberate. Okay, I have 0.00583333 dot 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 dot, and the 3's keep going, and my calculator can't show infinite theories, but it keeps going, and it's one of those 0.33333s all the way down. What do we do here? We can round it, but where are you going to round it? 3 decimal places, 4 decimal places, and I want to just say right now, when you round a percent, it may be easy for us, but that means thousands of dollars are going to be, people are going to get ripped off to the tune of thousands of dollars, maybe even more. So you don't want to round it, not the percent. So we do not want to round this. And even the value on a calculator has, it has to terminate because it has limited screen space. So even that's not going to be accurate for us to write out as many 3's as it has. I don't want you typing in all those 3's and looking at all those digits. Instead, we're going to leave it like this. So the computation we're going to be doing, and I'm going to go over here to do it. I'm going to be entering 4320. 1 plus, and I'll use the parentheses that I mentioned. I'm going to show you right now. 0.07 divided by 12. I'm going to leave it like that. And like I said, the exponent's fine. I don't want to do the 12 times the 10. I can use that as 120. So I'm going to type it in like that. I'm going to pause it here, and then we'll get our answer. A more accurate answer than if we had rounded that periodic rate. So let me show you how we're going to enter this. How it shows up on our screen for those of us that have the 83. Is that right? 4320. Okay. You can omit the multiplication symbol. You can omit the leading 0 in that. All of that applies. The exponent's the main thing I'm worried about. And I suggested that you just raise it to the power of 120. And your screen is less elegant, and so you can see that it wraps around. And so I would do 120 there. And that's fine. Nothing different about that. Yeah, same. Okay. I did want to talk about what happens if you try to get away with not multiplying your 12 times 10, your n times t. That is an issue that you have to worry about. I would just do it. It's doable without, but you have to be conscious of order of operations. And it's hard for me to show it here because it's just writing on one line the issues associated with this. Okay, if you raise it to the 12 times 10, it's not going to treat both of those as in the exponent. It's going to treat, right there's your caret, and it's going to treat it as if it's to the 12th power. And it's going to treat the times 10 as the separate thing, like on that last example, like the times 3. It's not going to do it correctly. And it gives us a wrong answer. So your best bet is to just do the 120, the n times t separately. If you really want to not have to do that, it's fine. But it's tricky. What you have to do is you have to show the calculator that you want to do that computation as one thing first. So you need to start introducing parentheses as grouping to tell the calculator you want it to do 12 times 10 first as a grouped operation. Close right there, it's saying do that as one thing via the grouping of the parentheses. It'll get 120, and then that exponent it'll be raised to the power of whatever you get after you resolve that grouping step. And then we get it correctly. So if you want to do that, that's fine, but you have to be real conscious of order of operations on a TI-83. My recommendation is to just do the n times the t as one single exponent first. But the main thing is, the other main thing is leave that unresolved, again, for that same purposes we were talking about with the other folks with the 84s. Okay, that's all I got for you guys. Do this 4320 times And here we do need to use parentheses because we're not going to just write one factor. We're going to write an expression involving addition and division. 1 plus 0.07 divided by 12. And then make sure whenever you use an open parentheses, you close it off at the appropriate place. And that's the factor, but instead of using 1.00583333 and then having to chop it off somewhere around it, we'll let the calculator deal with all those digits by leaving it unevaluated, meaning just as is, unsimplified. Exponent, I suggested for the exponent that's not an issue, so we might as well just multiply that separately, which we did, and then use the total of n times t, 12 times per year for over 10 years, 120 compounding periods. And we get our answer, $8,681, and we're going to round to the nearest penny, the nearest cent. We got to round properly, so 73. We're going to round it as 3 because of the digit to the right. This 7, it's going to round up, so we're going to have 0.74, 74 cents. All right, let me elaborate a little bit on, so let me clear my screen and do it again. First of all, when you mash two things next to each other without a symbol, it's assumed to be multiplication, and the calculator does that as well. So you could have omitted the multiplication symbol. I still don't want you to do this. I still want you to leave it as 1 plus 0.07 works just as well as 0.07, so you can omit that leading 0, but don't forget that 0. That's important. Divided by 12. Raise to the exponent. And for the 84s, because you're getting this cursor up here, you can, in theory, do n times t and just, not actually simplify it first. So that'll work because both of these are, this whole expression is in the exponent, so it's going to do 12 times 10, 120, and treat that as the exponent and get us the same answer. Real quick though, since we're on exponents, let me just talk about that property of the fact that we could put an expression in the exponent. It's a separate problem. Let me do 2 raised to the 5th power, and then I want to multiply that result by 3. Now my cursor is in the exponent, and if I do multiplied by 3 now, that's treating it as 5 times 3 is my exponent, so I'm going to use an exponent of 15. This will be 2 to the 15th power. That's going to be a very large number. Let's say I didn't want that. Let's say I wanted 2 to the 5th, and I wanted to take that result. 2 to the 5th is 32, by the way. And if I wanted to take 2 to the 5th and then multiply the 32 by 3, I got to get that cursor down out of the exponent. And what I do is I hit the right arrow key to do that. It'll come up later where we have to do this. Now it's on the ground level, and now when I do multiplied by 3, it's going to treat it as separate. It'll do 2 to the 5th, which is 32, and then take that result and then multiply that whole result by 3, which will give me 96. So that's how you're going to get it out of the exponent. The cursor out of the exponent is hitting the arrow key. Okay, the 83s are a little bit tricky, but if you have an 84, TI 84, you're good and you can skip that section, but I'm going to do an 83 lesson real quick and talk about a few things that they have to be concerned about. Okay, so we have $8,681.73, but the 3 rounds up to a 4, so 74 cents is the amount. For your notes, leave that unevaluated. I'll say unsimplified, that might be a more familiar term. Leave that unsimplified, but go ahead and multiply the n times t up there for the exponent. Make some sort of note for yourself on how you want to handle this situation. Again, multiplication gives you a whole number, so that's fine, and we want to use that because it makes it easier for the calculator, for us to not mess up the exponent on the calculator, especially for the people with the TI-83. This one, we don't want to do any rounding, division. Oftentimes, most of the time, we'll end up with something weird like that, and we want to keep it as accurate as possible, and that's the best way is to enter it unsimplified into your calculator. All right, that's that example, and then I think we're not good. We got to do more examples. I want to make sure you're clear on it, but I think I've ironed out all the things to worry about, and then so we'll do more examples real quickly, and then do another type of problem, and then APY. Okay, let's just get some practice doing this. I've covered most of the issues, the little tricks and things to worry about that come up when you're doing compound interest. Suppose we make a $900 deposit. In an account, no comma, that earns 5.25% annual interest. Period. So we're going to have a weird percentage now. We'll talk about that. This is, like I said, banks do use 1/4% and 3/4% and 0.5%. We've done half. I maybe did 1/4 so far, but we'll talk about it. Notice I didn't put the compounding period because that's going to be left open for now. Where am I at? How much will we have in the account? After 15 years, if interest is compounded, and here I just want to make sure we get a lot of practice, so we'll do a couple of these with that same information, but we do semi-annual, we'll do quarterly, and then daily. I'm going to have you work these on your own first, and then I'll go over it. But before we get to that, let's make sure we can get the correct R, the rate, because this is a newish thing. 5.25% annual interest. Okay, so in your notes, I'm going to take that and I'm going to say R is equal to, that's your rate, as a percent. We won't need the decimal form of the percent, but it's technically equivalent. We just, to work with, we need the actual mathematical equivalent of that, which is the decimal form. Alright, so it's going to be, so before we move the decimal, we got to figure out how to rewrite the mixed number as a decimal. So 5.25 is going to be 5 point something, 5 and some change. That's still the percent, so make sure you write that in and know that we have, that's not the conversion yet. We will need to move the decimal point 2 places after. But we got to figure out how to express the 1/4 as that decimal in the box. You literally do on your calculator. If you don't know it already, if you do, that's fine. It is 0.25, but you just can do 1 divided by 4 for that 1/4 right there. And then, so 1/4, it'll show up on your calculator like that. We'll give you 0.25. I don't know if you can see that. Can you see that? Nah. 1/4 is equal to 0.25, and so that's what's going to go in the box. 5.25 is 5.25. Sorry, 5.25 is 5.25. 5.25% is 5.25%. The decimal form of that percent is we have not done yet. You get that by moving the decimal point 2 places to the left, 1, 2, and we're going to get 0.0525. If you recall, when you have a single digit percent, it occupies that second decimal place, that's 0.05%, and then the 25 is change, fraction of a percent. That's where they end up. That's the third and fourth decimal place. Anyway, that's what we're using. From there, I want you to pause and then work these out using that R and the appropriate information that you have here. And whenever I do that, I say pause here and then do it on your own. Make sure you are. You need to start getting your hands dirty and start working with these things to get to practice and put the pieces together. I think I've already said this, but make sure you do it, and then to see it done after you've already worked on it will help you with the homework. If you just watch, passively and then jump into the homework, you're going to struggle with that first homework problem and text me, and I'm going to have to go over that first problem to get you going with these. Let's get ourselves going with these examples that I'm specifically putting up here to get you going with this process. Pause here. Okay, but as far as I'm concerned, I'm going to pretend you paused for 3 or 4 minutes and worked on it, and have all your answers, or got stuck and know where you're stuck and realize now, oh, I wasn't clear about this. Let's clear it up now if you were stuck. Alright, I'll write the formula once. I'm not going to list everything out ahead of time like I told you you should. You should, but I'm not going to practice what I preach in this instance. We're moving along a little quicker now. 900 is your principal. 1 plus our R, we just spent a little time figuring out it's 0.0525. Oh my god, that's ugly. But we'll work with it. Oh, what's N? Semi-annual is N is equal to 2. I should have wrote that in. Divide by 2, and then N times T. 15 years, but twice a year. I wrote that. Yeah, that's right. 2 times 15. Okay. And then what I'm going to actually type into my calculator. I'm going to leave this unresolved. It might not be that bad, but I don't know how that's going to work out. I don't want to do any rounding. But I will resolve that to exponent of 30 and then work with that. That's what I'm going to type in the white like I did before. I'm not going to show you the calculator. If you need me to, you have to text me individually and request it. I'm going to assume we are all somewhat good with that at this point. Raised to the 30. Okay, I got 1, 9, and keep in mind it should, it should be 15 years is a long time. I was going to say it should be close to that, but it builds up quite quickly into 1,958.11. I'm going to round that down to, and keep it as 11 because of the 2 next to that. So that's it, $1,958.11. If you leave it in for 15 years, it does build up at this completely unrealistic rate of 5 1/4%. Anyway, that's semi-annual. I'm going to have to make a little space for quarterly and daily, so let me just smooth that over. I'm not forgetting about it, but I'll have to erase and make room for the last one, the daily. Quarterly, everything's the same except for N. Quarterly means 4 times a year, you're using N is equal to 4. Everything else is the same. Formula's the same, so I'm going to just jump straight into 900 times 1 plus 0.0525. Here's where 4 is now N, and then 4 times per year times 15 years is what we're going to be doing. Leave my R over N unsimplified and enter it like that, but I will go ahead and do 4 times 15 on my calculator. Press, press, press. Oh, it's 60. Okay, let's go. Oh, I got an error. What did I do? What did I do? One, 9, 6, 7. Ooh, a weird one. Let me write it out. I said I wasn't going to show you rounding, but ooh, I better do it on this one. I give you some practice problems like this on the rounding exercise or homework, where it does carry a 1, and it gets weird, real iffy. Rounding to nearest cent is right there at the second 9 there, or that's the third 9 overall. The 7 tells us we're going to round up. This is a good exercise anyway. I got to bump up that 9 by 1. 9 plus 1 is 10, carry a 1. 1 plus 9 is 10, carry a 1 a second time. My decimal point is there. 8. And then I'm good from there. There we go. $1,968 exactly, just by sheer coincidence, when we rounded up that 99 cents. Because of the 7, rounds up 1 penny to a whole number of 1,968. Since it's exact, you can leave it like that, or you can put the 0.00 to emphasize its exact amount. Either one's good. But make sure you, for these, you're leaving me the pennies, because I need every penny I can get these days. All right, daily. And I have a few more things after that. 365 days per year. All right. N down below, R divided by N, so I'm going to be dividing by 365. This will be 365 days per year times 15 years. It's going to be a huge exponent, but it gets offset by the fact that this periodic rate gets smaller and smaller the more you're dividing it up, so it's not going to be significantly different from this. I do want to, as before, leave that as is, but go ahead and do that, and that I actually don't know off the top of my head. 5,475 compounding periods. That's every day for 15 years. That's how many days in 15 years. And let's do this. Four, 7, 5, 1, 9, 7. Okay, this one looks possibly as weird as the last one, but it's actually not. 0.993317 is what I'm seeing. Same thing, I do got that 99 cents. I'm going to round it to the cent, but this one's going to round down. So I'm going to leave that alone. I'm not going to do the bumping up by one and having it carry a bunch of ones. This one's going to stay at 99 cents. Okay, if you notice, it's a little more than, let me circle this one. The more compounding you do, more often you do it, you get your interest immediately put in, and then you start earning interest on the interest. And the more often that happens, the better it is for the person getting the interest. So you see you get a little bit more money if you compound it more often. So that's a general trait of compounding. Okay, I got more to do, but not much. Okay, next example is going to be a little twist on what we just did. So, suppose a parent wants to have $45,000 for college tuition on their child's 18th birthday. If they find a bank that offers .75%, which is realistic for certificates of deposits, other investments that you can do with the bank, compounded quarterly. How much should they deposit? At their child's birth. So the idea here is they're going to take a bunch of money, put it into this account that earns 0.75% interest compounded quarterly, and they want to have exactly, or at least, but we'll treat it as exact, $45,000 exactly 18 years later. So this is the opposite. We don't know what the principal is that we have to put, but we know the end result, the amount that we want at the end. So, let me list out the things that we have. Our principal is not $45,000. We are not depositing that. We want to know how much they should deposit at their child's birth. One lump sum. Now in reality, you usually pay into these sorts of things, a college fund, gradually, and we will actually get into that when we talk about annuities, probably in the next lecture. And it'll be a little bit more complicated, but here we're just getting a feel for this idea of interest, which applies to the annuities. But we're going to treat it as one lump sum of an unknown amount to be deposited. Our rate, it's not 0.75, it's 0.75%. That's not 75%, so make sure you don't use, this is wrong, make sure you're not using that, because that's 75%, and that's insane amounts of interest, and they are not giving that to you. They're giving you a fraction of 1%, 3/4 of 1%. You move the decimal place 2 places, 1, 2. It's not even a single digit percent. Again, it's a fraction of a percent. 0.0075 is your rate. You are doing it quarterly, and it's 4. T, well, you're waiting exactly 18 years from birth to their 18th birthday, presumably. And the amount you want at the end, this is the first time I'm going to actually write an A, because this time we know we want to have $45,000 at the end of the 18 years. Okay, the formula still applies, but it requires us to solve for a missing P. Let me copy it down. Okay, and let's start putting in what we have. But again, $45,000 is the amount you want to have after the 18 years. P is unknown, so you leave it as an unknown P. We're going to solve for P. Since it's P times, we will be dividing. They don't write that in the formula, but that's multiplication there. So to solve for P, we'll be dividing by whatever this factor is with the exponent. 1 plus 0.0075 divided by 4. And then 4 times 18, I'll write it as 4 times 18, but I will be resolving that in the next step. Here again, we probably have to still leave it unsimplified for this periodic rate inside the parentheses. 4 times 18 is 72. Yeah, 72. Okay, in theory you could work this piece out and then round it off, and it's not going to be as accurate. So let's see what we can do about a more precise answer by just leaving that whole thing as is and entering it in the calculator the way it is. But we can't do it here because we still have to get our final answer, we have one more step. So we normally divide to cancel that. Separate example. If you're solving for P here, you divide by 3. It's P times 3. They might even write that as 3P, but it's the same idea. It's multiplication. It doesn't matter which order they put the 3 and the P. It's a product. And you divide by 3 to cancel that and solve and get P is equal to 4. In that completely fictional situation. But the operation for this one is the same. You divide by this factor right here, this whole thing. What's it equal to? I don't know. I'm going to find out later. In fact, I'm never going to find out because I'm just going to use this as is. Divide P times this by this exact same thing. And it's going to cancel that entirely. But you have to do both sides. So our answer will be P by itself is equal to 45,000 divided by whatever this ugly thing ends up being. Okay. And we'll have P is equal to, and then I'll enter that. Well, let me write out what we're going to try and enter. When you're trying to, do your exam or even your homework, you write out some steps, you get to this stage, and I anticipate some people will not be being able to put in the calculator properly and correctly. I'm a little more forgiving of that because it is a complicated thing. It's better if you have software to work with. We're working with a very crude tool, the TI-83, for computations like that. But we'll try to make it work. But the main thing is you understand this process and get up to here. Those will be for like points in an exam. That'll be most of your points there, and maybe I'll deduct 1 or 2%. Sorry, 1 or 2 points off of maybe like a 6-point problem if you enter it incorrectly and get a wrong answer here. But I also recommend that you check your answer. So I'm going to pause and go in my calculator. It's doable to just write that expression in as is. When you have such a complicated denominator, it's always sketchy and you're not sure if it's going to resolve it right or evaluate it correctly. So I'm going to recommend something that will apply to both 84 and 83. I'm going to do that denominator first and figure out what it is. Now I said I didn't want you rounding it, so even though we get an answer, we'll just deal with it on the calculator. So you'll see in a bit, but let's see what's going on with this. Okay. 1 plus 0.0075 0.0075 divided by 4. Close it off, so you have that factor. We're going to raise that factor to the 72nd power. Okay, and that's going to be your denominator. So we want that on the bottom of the fraction, but I haven't written it in that way, and I'm not going to, not yet at least. So I'm going to enter. And so ultimately, the equation that I have on the board is 45,000 is equal to P times this. And then therefore P is 45,000 divided by this. Okay, now here's the thing that's on both calculators. There's our answer that we want to divide by, and we could type it all out manually. We could round it, but the rounding will give us an inaccurate figure. It'll lead us to errors and not be super accurate. So I want you to be able to do this. I want you to be able to refer to this previous answer in our computations, and that's where ANS comes in. ANS stands for the previous answer. It has to be the answer that you did just before. If you do something, other computation, in the meantime, it's going to be that. It's going to be literally the last output on the page, which right now is this. Okay, so you got to be careful. You can't do other things in between. Anyway, what do I want to do with the previous answer? I don't want to put it yet. I'm going to do second answer, but not yet. I don't want to put it first. I want to put 45,000 first. 45,000. And then I want to divide by, and I want to divide by this, 1.144392119. And you can type that in manually, but since it's the previous output, I can literally just do second and then right there. And that ANS stands for 45,000 divided by the previous answer, which is right above. That's what we want to do, right? Okay. And then, yeah, real quick. It's the same on TI-83. Yeah, but that's how we're going to approach these problems. In fact, I'm not going to do the TI-83. It's the same thing. Okay. Okay, so I just showed you on the emulator on my computer, which is like a fake virtual calculator on the computer. Now I have to actually do it in real life because my answer's way over there and I didn't write it down. But I'll walk you through it. I'm going to do this bottom piece, just that. Parentheses 1 plus 0.0075 divided by 4 raised to the power of. For the 84s, I'll get a box. For the 83s, I'll get that caret button. 72. Parentheses 1 plus. The parentheses is important still because that exponent has to apply to the whole thing after it's simplified down to a single factor. 0.0075 divided by 4. Close parentheses and then raise to the power of 72. Okay, and then that's about 1.144, well, I'll write everything that I see, but you don't need to copy that down. And then what I want to do is do 45,000 divided by that, and I could type in all those numbers. That's a valid way to do that, but it's better for me to then do 45,000 on my screen, divide by, and then use the previous answer, which will refer to that. So this previous answer is the secondary function of the negative symbol. And I got 39,322. Yeah. So P is equal to, and this is what I computed right here, 39,322 down to the penny. So it's going to be 18 cents, but it rounds up because of the 6. So I'm saying 0.186. That rounds up to 0.19 when I round it off to the nearest penny. And so $39,322 and $19 is supposedly what we need, and then via the interest that you earn on it over the 18 years, very low interest rate though, a realistic one, but it'll take 18 years for that to build up to a nice $45,000 for your kids' college tuition. Let's check it. Yeah. It is a rounded figure, so it may not give us exactly 45,000, but that's the best we can do. But let's check it. Because now we can pretend, let's see what amount we get if we use that as the principal. Let me write it out. Okay. The same formula we just used, except now let's pretend we don't know A, but we are assuming that this P is correct. Or actually, we're going to verify it's correct. We're going to use that, 39,322.19 times 1 plus your interest rate divided by 4 quarters raised to the 72 power. And now we can do the computation we did earlier. and see if it comes out the way we want it to. And we want it to come out to about $45,000. Ooh, okay. Yeah. I get 0, 0, and then 4 is after that, so it does round down and stays at 0, 0. I wouldn't be surprised if in this situation it comes out to 1 cent or 2 cents. It's a little bit off from the goal that we want, but that's just because you did some rounding here, and therefore when you go backwards, it's going to be a little bit off there as well. And that's fine, but this is a good indication that we've done it correctly. If you mess up this computation here, which is tricky, it can be tricky, you usually end up with an answer that's way off, and you'll know something went wrong with probably that process. So practice that with the examples that you have on your homework. Okay, next we're going to talk about APY. Okay. The annualized percentage yield. Abbreviated APY is a very common thing to see in banking offers. It's basically if you have different rates compounded at different compounding periods, it's hard to compare them and see which one is a better deal for you. And the APY is a way of being able to compare them apples to apples and easily seeing which one is a better offer and going to get you more money. So is the rate that if compounded annually is equivalent to, or will yield the same amount of money, yield meaning get in, equivalent to the given offer. Okay, and there's a formula for it. You'll have your notes during exams, so you have to memorize these formulas. It's not pretty, but based on what we've been doing, like the last problem, it's not that bad comparatively. It's going to be 1 plus r over n, raised to the n power minus 1. We're going to use that for now just blindly, but when I get to examples, I'm going to show you what it's actually doing and give you some sense of where that's coming from. But as of now, let's just go with that. Okay. And before we get to examples of computing APY, let's talk about the reason for it. So let's see. This is not finding APY yet. Oh, I'm going to erase this because I want to use the whole board for this example. Okay, but anyway, that I will need somewhere. Let me just put it in the corner. Okay. Suppose we have $1,000 to invest. Which offer yields a greater return and I'll say over 1 year, after 1 year. It doesn't actually matter what time, as long as we're using the same amount. We could do after 3 years, after 4 years. It won't change our decision. Whichever one is better will be better for any period of time. I'm going to do 1 year just to keep it simple. Oh, and my two offers are 12% compounded daily and 12.3% compounded semi-annually. So the idea is if you see two banks and they offer, competing banks, and one offers you that and one offers you that, which bank are you going to go with? You can't tell just by looking. I mean, 12 versus 12.3, this is the greater rate, slightly greater. But remember that compounding more often also yields better returns than compounding less often. So you have two offsetting things, and it's impossible to tell which one is a better one. And as of right now, we're just going to grind it out and compute. The $1,000 gives us what at the end of the 1 year period. And again, we're going to do 1 year, 1 year, but if we did 5 years and 5 years or 17 years and 17 years, it would still be the same. It's essentially the one that is better will still show up regardless of the time frame. Anyway, let's do this. I'm going to go a little bit quickly, but it's $1,000 principal. We're doing this one, so it's going to be 0.12 divided by daily is 365, and then 365 times 1. It's 365 compounding periods per year, but it's 1 year, so 365 times 1 is just 365. We'll compute that, but let me just set up this one at least. Same thing, but different n. Sorry, different rate and different n, different r and different n. 1 plus, this one is 12.3%. So a little bit higher annual rate, but that's going to be offset by the fact that you are just dividing it by 2. And then over 1 year, semi-annual, 2 times 1 will just be 2. Make sure you understand that setup. I'll compute it for you. You can if you want, follow along. You can pause it and do it if you want. I'm not worried about it at this stage. I want to get to the APY situation and talk about that, so I'm going to rush through this a little bit. 1 plus. I got 1127.47. Okay. Okay. The other offer, $1,000 times 1 plus 0.123 divided by 2 raised to the power of 2. 1126.78. Okay. So again, slightly higher annual rate means usually that gives you more money. Compounding more often gives you more money, and so this one has a higher rate of compounding, this has a slightly higher rate. Which one is better? Well, despite the fact that this is 12.3 versus 12%, the daily compounding versus semi-annual makes this one the better deal. So 12% daily, I'm going to abbreviate or shorten it, compounded daily is the better offer. Alright, that was pretty tedious to figure that out because we had to just grind out the computations. But APY, we're going to get the APY that's equivalent to this, we're going to get the APY that's equivalent to that, and then we'll be able to compare just as easily. But the benefits of that is banks are required by law to show APY, so you don't have to do this crap. They will do it for you, and they'll make the comparisons easy instead of trying to, trick you into getting the one that's a better, worse offer. All right, let's calculate APY for both of these. Let's see. It's important that we kind of remember this one is a better one, but we're going to verify that via APY. I'm going to erase these computations we don't need anymore. And new instructions, but the same two offers. So I'm going to leave them on. But reproduce them in your notes. So example, calculate the APY for the following offers. Alright, we'll just do this blindly and follow the formula. And then we'll talk about what it means. And going back to the definition. But anyway, it doesn't involve principal, it doesn't involve time, because again, the $1,000 that I used could have been any amount as long as it's equal. The time frame T could have been, number of years could have been anything as long as they were equal. It was a rate and the compounding period that made a difference. And that's all we need there. APY is going to be equal to 1 plus r is still this, n is our compounding period, 365 days, and we're going to raise to 365, and then we're going to subtract 1. And we'll talk about where that's coming from once I work these out. I'll come back to the computation. It's not that bad, but I want you to set up this. I want you to pause and set up this one. Just following this based on this information. Again, you don't need a P or a T to this APY conversion. Okay, I'm going to assume you pause and set it up. 1 plus 0.123 divided by 2 for the semi-annual compounding, raised to the 2 power, and then minus 1. Okay, and I'm going to type this all in once. We just have to tack on a minus 1 at the end. Here's where, when you're in the exponent, you got to make sure you get it down to the ground level. I think I might want to go on show you on the actual calculator. I'm going to show you, just to remind you of that issue. But I'm going to show you on both. And I'm just going to do the first one, and then the second one, the 12.3 semi-annual, I'll just do it on the board. But here I want to remind you, okay, so for the 84s, we got to watch the exponents. 1, parentheses is important, 1 plus 0.12 divided by 365. Close that off, and then raise to the power of 365. Okay. When I hit the exponent button, it gives me that raised cursor, and I enter my exponent there. And there it is, except I'm not done. I have a minus 1. And here's the issue I mentioned earlier, but it's important now because it's part of our computation. We don't want to just type in minus 1. Now I'm going to do it, and I'm going to show you what happens. It's incorrect. The minus 1 is up here in the exponent. So it's going to subtract 1 from 365 and use an exponent of 364. That's not what I want. I want it to use this exponent, and then after minus 1, I want it to be on the ground level. So this one will give me the wrong answer. I'm going to delete that 1. I'm going to delete that minus sign, but I'm good there, 365. I want to get that cursor down to the ground level, and here's where I use a right arrow key. I think it's indicating that's what you should do. That symbol that's blinking is right arrow maybe. Either way, we are doing right arrow to get it down to the ground level. And then it's just a minus 1. So it's a very different computation than what I had previously. This one being the correct one, the last one being way off. Hit enter, and that's it. And so we're going to keep some decimals and convert it to a percent. Anyway, let me. Okay, the 83s actually are fine with this because it doesn't put the cursor in the exponent. So I want to do the same computation. The first one, 12% compounded daily. 0.12 divide by 365. Close it off. Okay. You raise your exponent there. 365. It doesn't give you a box that's raised, so to get it down to the ground level, you don't have to worry about it. It's already on the ground level. It's trickier if you have something in your exponent. If you want it to be in your exponent, you needed to use parentheses around your exponent. But here, tacking on a minus 1 will be treated as not the exponent. The exponent is 365. The minus 1 will be done after, based on your PEMDAS order of operations. So you're actually good with this. For the first time, it's to your advantage to have this calculator. All right, and I'll do the other one on just straight on the board, but same idea. Okay, I forgot to mention, because I'm just going to have you do a rounding thing. Round percentages. Normally we do to the 10th of a percent, but when we get to banking rates, they will give us 2 decimal places. And because these are going to be so close and we want to make a comparison, we might need extra precision. So round percentages to 2 decimal places. I forgot to write that. If you could throw that in somewhere in your notes, I'll try to remember to put it on the next example. Anyway, we did this on our calculators, and I got 0.12747, and then a bunch of other digits. Okay, and as usual, we're going to round to 2 decimal places after we move the decimal point. So it's going to be 12 point something. It's always going to be very close to these. But compounding daily means you actually get a fraction of a percentage more. I'll spend some time on this. Okay, percent. This time, unlike the 10th of a percent, I'm going to be to 2 decimal places, so we're actually going to keep 2 digits after the decimal point after we've converted to percents. It's going to round up because of that second 7. And so that's your APY for this offer. And the banks are required, if they give you this weird thing of compounding daily 12% and you don't know whether that's better than the other offer, they should be, by law, publishing the APY equivalent of that so that you can compare to the APY equivalent of that. And that'll be an easy, straightforward comparison on which is a better offer. Whichever one has a higher APY is a better offer if you're the one collecting interest. Okay, this one I gotta do, okay. Same idea. If you have the TI-84, make sure that cursor comes down when you do the -1. Do this on your own and compare it to mine's after. I can watch that -1. .12678.225. I'm going to move it 2 decimal places. It's going to be 12.6, and then I'm going to round there essentially. I'm going to skip a few steps here, and so that's going to be 12 is the whole number percentage. Those are my 2 digits after the decimal point. I'm going to round it to 7. It rounds up. 12.69% APY. Which is the better offer? Looking at this, it's hard to tell. APY is an easy comparison. This is the better offer. Okay. Because this is the rate at which you would get the same amount of money if you had invested compounded annually. So let me elaborate on that. That might seem a little confusing. So let me take a moment to just focus on one of these. Okay. So the idea here is that if we invested an unknown number P, an unknown amount P, under these circumstances right here, 12% compounded daily, what would that be equivalent to? What rate would be equivalent to get the same amount of money is if you were compounding annually this. So this is going to be, in this case, it's going to be the 12% compounded daily. And on the other side, we're going to look at what happens if you take the same principal, the same T. What rate would be required here to make the amounts equivalent, to make these two offers equivalent? So this is not just going to be any rate, it's going to be different from this one. This is our APY rate. It would make it equivalent that if it were compounded annually to the 12% compounded daily. So we're basically going to be setting that equal to that. The amount that you would get via this offer versus the amount you would get if you compounded, if you use this APY raised to the T power. That's APY. You're replacing R with, it's an unknown R, not the same as the other side. This is 12% a daily, this is an unknown APY, and we want to find out what APY will make them equivalent. That's the idea. Alright, and this is like a proof almost. We're going to solve this. The principal doesn't matter because it cancels out. The time doesn't matter because it sort of also cancels out. Technically, algebraically, you need to raise both sides to the 1 over T power. We aren't really getting into solving exponential, so that's not super important. But the idea is that T's cancel because they're on both sides, and you end up with 1 plus 0.12 over 365 to the 365 power. That T's gone, and you also cancel out that T, so this side is just 1 plus APY. No need for parentheses anymore because there's no exponent. That cancels with that. Okay? And then you want to solve. You want to know what APY will make these two factors equivalent, because that means it's the same amount of money, and obviously you just want to get rid of that 1, minus 1. The minus 1 won't go inside here because that's already affected by the 365. That minus 1 will just come off the end. And that's a computation we did to get whatever I had, 12.75. That's the idea. That's your APY. Sorry, technically the APY is solved on this right side. But that's where that formula is coming from, except we don't have actual numbers there. We're working with generic R's and whatnot. But that's what it's doing. Seeing an equivalent rate that if compounded annually will give you the same amount of money, the same yield as 12% compounded daily. Okay, let's wrap up by just making sure you can do a couple of quick APYs without all this lead up and extra stuff that we just went through. And then we're done. .5% compounded monthly. And then I'm going to give you a weird one, 3 1/4% compounded quarterly. And all you're doing is following this formula here, going straight to the formula. No need to solve it like we just did or do anything more extensive. We now have a formula. We're semi-convinced we know where it comes from and how it works. Just go straight to the formula. Your answer should be very close to this. Again, 6.5. The monthly compounding gives you a little bit extra money, and so it should be a little bit higher than that. I should be a little bit higher than that. So you should get something close to the AP, what's called the APR. This is your APR. We're looking for the APY that makes apples to apples comparisons. Pause here. Work them out, both. Please do that. Whenever you're ready, unpause, and here we go. Watch your placement, 2 places, 0.065. Monthly is 12. And that's it. 1 plus R, our rate in decimal form of the percent, divided by the compounding period, or number of compoundings per year, 12 per year. N is there as well, and then minus 1. Again, watch that exponent and bringing the minus 1 down to the ground level to do that. Ooh, and then, oh man, same instructions, 2 places please. I just promised you I would remember this and I didn't. I'm so sorry. Okay, 2 places. My second decimal place when I do that will be there. I'm going to round at that 9. I'm doing multiple steps in one. It's going to round up because of the 7. Yeah, let me do it more carefully. This one's a weird one. It'll be 6.697 ... percent when I move that decimal point. 2 places to the right this time, going from a decimal to 8%. I'm going to round there because it's my 2 decimal places. This 7 tells me I'm going to round up, but that means I'm bumping up to 9 by 1. .70%. Okay, very close to 6.5%, but a little bit extra because you're compounding so often, 12 times per year. All right, completely different. Ooh, let's talk about that. That's 3.25%. We do one similar for the 1/4%, and then I'm going to move it 2 places, and I'm going to go straight here and do it. 0.0325 is the decimal form of 3 1/4%. Quarterly is 4. And we'll do the 2 decimal places that I keep forgetting to specify. Okay. Then I got 0.0329898 dot dot dot. When I do the 2 decimal places, 2 places, and a decimal will be there. Where I'm going to round is at 8. It's going to round up, but let me do it more carefully. 3.2898 dot 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 percent. I'm just doing dot 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 because I just need digits up to, I need to round there, but I need to see that digit to the right, so you need to keep a little bit more than you're keeping. Specifically, you need that digit to the right to know which way you're going to round. In this case, up. I'm going to bump up that 8 by 1. 3.29%. Yep. And again, it should be very close to 3.25%, but a little bit extra for the compounding quarterly. Again, the APYs are what you would need to APYs are less compounding, so you need a little bit more there to make it equivalent to one that compounds more frequently. All right, but anyway, you just got to do some APYs using that formula. You will have your notes during the exam and presumably during your homework, so it shouldn't be something you feel the need to memorize. All right, that's it.